Hello and welcome to my presentation about the security of cyber physical systems. My name is Armando Capote and I will be discussing the security aspects that surround cyber physical systems. In recent years, cyber physical systems have emerged from traditional engineered systems in the areas of power and energy, transportation, healthcare, and manufacturing, among others included in the list below. By introducing communication support in those systems, they have become more flexible, performance-oriented, and responsive. In general, these cyber-physical systems are also mission-critical, being that their availability and correct operation is essential. A cyber-physical system can essentially be described as effectively integrating cyber intelligence and connectivity with physical components in our everyday lives, giving them the ability to process and provide computing power while also being network connected in order to provide a service much like the Internet of Things provides. Some of the industries that cyber physical systems can be found in are communications, consumer, energy, infrastructure, healthcare, manufacturing, military, physical security, robotics, smart buildings, transportation, and many others. Cyber-physical systems are essentially feedback systems consisting of being networked and distributed, adaptive, predictive, intelligent, and real-time. I will discuss each in a little bit more detail. Network-controlled theory assumes continuous or discrete timing and signaling, where the controller continually or periodically observes the physical subsystem and continually or periodically provides actuation to the system. In a typical cyber-physical system architecture, the signaling is mediated by software and networks that do not have such continuous periodic behavior. Adapting control theory to handle the realities of software and networks is an important cyber-physical system problem. Adaptive. Cyber-physical systems are typically closed-loop systems, where sensors make measurements of physical processes. The measurements are processed in the cyber subsystems, which then drive actuators that affect the physical processes. The control strategies implemented in cyber subsystems needs to be adaptive, or responding to changing conditions, and predictive at the same time, anticipating those changes in the physical processes. Intelligent. Intelligent systems are ones that emulate human capacities for learning, understanding, or perception. In the context of cyber-physical subsystems, there are particular opportunities and challenges associated with controlling or predicting the behavior of such systems and how their behavior affects overall system behavior. Real-time. Cyber-physical systems typically include software that has timing constraints, including tasks that must be executed periodically, deadline constraints, or latency constraints. The classical field of real-time systems, which provides operating system level scheduling strategies, plays a central role in this. A key problem that is specific to cyber-physical subsystems is that traditional programming models only indirectly specify timing properties, typically by associating priorities with tasks. So a key opportunity is to develop programming models for time systems, and most interestingly, for distributed time systems. In the attached image, you will see some examples of cyber-physical systems. I will now go over some of the industries and markets that cyber-physical systems can make an impact and how they make that impact. In communications, digital control and the contention for physical resources such as radio spectrum and fiber channels, communication systems are intrinsically cyber-physical systems. Cellular backhaul, sensor networks, and wireless networks are all examples of that. In the energy industry, energy production, distribution, and optimization are all cyber-physical problems. For example, the smart grid combines multiple electric power production plants with a varying loads using dynamic load balancing and dynamic pricing with demand response strategies. Smart buildings integrate sensors, typically wireless, into control systems for lighting, HVAC, heating, ventilation and air conditioning, and safety, fire monitoring, and evacuation. In the infrastructure industry, society depends on critical infrastructure, electric power, water, roadways, etc. Cyber-physical systems can help manage and maintain such infrastructure by providing disaster recovery, structural health monitoring, water distribution optimization, and water safety monitoring. In healthcare, many healthcare systems are cyber-physical systems. In hospitals, for example, information from many sources like bedside monitors, lab results, and practitioner observations are combined to inform interventions. Today, many components of the health system operate in isolation and some limited integrated solutions are available. In the future, they will be combined into networked, closed-loop systems with humans in the loop to provide medical workflows and patient safety. Emerging technologies aimed at enabling remote care of patients will provide care practitioners with information on how activities of daily living affect healthcare and allow practitioners to make more informed decisions about interventions. The combination of these two currently separate aspects of healthcare would transform the healthcare system into one large and complex and safety-critical cyber-physical system with many advantages as well as challenges. In manufacturing, manufacturing systems that include robotic machinery, embedded vision, or any computer-controlled actuation are cyber-physical systems. For the military, there are many aspects of cyber-physical systems that are used in different weapon and infrastructure planning and procedures. Physical security. Electronic physical security systems are cyber-physical systems. For example, card access control systems via database records or a data store on a smart access card link a cardholder's access privilege information with a specific ID card. So that presentation of the ID card at a door's card reader results in granting or denying access to the door based on the cardholder access privileges via electrical door lock control. Some access control systems utilize biometric readers to scan, for example, an eye's iris, a hand's vein pattern, a fingerprint, or a face. Networked video surveillance cameras run video analytics software to detect motion and recognize objects and people. In retail stores, video surveillance systems interface with the point-of-sale systems to help detect fraud at the cash register. Retail stores also use video analytics to monitor, via the presence and activity of people at the merchandise displays, the effectiveness of advertising campaigns. Robotics is a rich area of research and development that encompasses a range of intellectual topics from motion control to artificial intelligence, all relating to cyber-physical systems. Smart buildings. Smart buildings automation systems utilize a variety of sensor information to automate and improve building systems management. Daylight sensors automatically adjust room lighting to dim or turn off lights when sunlight suffices. HVAC systems utilize temperature, air quality, and occupancy information to adjust heating, cooling, and ventilation. Buildings are pre-cooled or preheated for occupancy based upon historical occupancy records, so that the application of HVAC conforms to actual building usage rather than fixed schedules. Elevator control systems utilize historical elevator traffic records to pre-position elevators closest to the floors where they will most likely be called next. This speeds up elevator response and reduces congestion in elevator lobbies. Transportation applications of cyber-physical systems include automotive systems, avionics and aerospace, elevators, escalators, and moving sidewalks, railroads, and traffic management. Major issues surrounding transportation and cyber-physical systems in that industry include safety, efficiency, and response to emergencies and disasters. The main goal of cybersecurity is to build trust in systems. Without trust, users would not know or have any way to prove that data actually meant anything. Four of the major portions that we need to focus on in order to ensure that cybersecurity is at the utmost forefront of our focus would be resilience of the system, privacy of the system, ability to defend against malicious attacks, and intrusion detection. Resilience is the ability of a material to absorb energy when it is deformed. In the context of cyber-physical systems, resilience is the ability of a system to continue operating satisfactorily when stressed by unexpected inputs, subsystem failures, or environmental conditions or inputs that are outside the specified operating range. Fault tolerance, fault detection, and adaptation are all techniques that promote resilience. Privacy is the problem of protecting information about humans from unauthorized access by humans or machines. This is essentially and most well known as the main goal of cybersecurity. Malicious attacks have increasingly become a pinnacle of technology. All networked computing systems face risk of malicious attacks. As cyber-physical systems networks become more open, they too become vulnerable. But even with closed networks separated by an air gap from open networks, there are still risks due to incomplete trust in suppliers and due to the possibility of accidental introduction of malicious code. Particular problems include backdoors, denial of service attacks, Trojan horses, and viruses. Intrusion detection is another system that must be focused on. Technologies that can be brought to provide this feature are embedded vision, motion detection and tracking, human detection, facial recognition, as well as timing models, enable detection of timing anomalies, which can reveal intrusion.